Hello, everybody. Welcome to Good Data Gone Bad, Bad Data Gone Worse. I promise there are slides on my computer. I'm just going to drink a Coca-Cola while we get started here. Because I have migraines, and I know that bright lights are one of my triggers. So I'm very happy to be here with all of you. Thank you for joining us. A slightly bigger version of me. My name, of course, is Renee. I work with data. I love data. I live in New York City. My most recent technical role was as a data analyst, and I was doing QA on a large data set of New York City real estate data. It was fascinating. You can tweet at me, and you can follow me on the Twitter. So this, of course, is a talk about how good data goes bad and how bad data gets worse. Data, in fact, can even just start off bad. So before we talk about data going anywhere, we need to think about what is data and all agree on what it is we're talking about. So data has common definitions. You'll see these three definitions. I will say them for the camera. Pieces of information with a format, facts used for making decisions, and information stored in and or used by a computer. We are not going to have a philosophical conversation about whether facts are real, whether there is any one knowable truth. That is an entire 50-minute conversation or a PhD. I think of data as a representation of some aspect of the world. And I think about good data as simply being data that is usable for the job that we have at hand. So there are a lot of things that people commonly think of as bad data that we don't necessarily need to address in this talk. If it fits, it's going to help us. If it's not fit, it's not going to help us. So thinking about why we want data that fits our purposes, we need to make plans. We need to do our operations. We need to look like we know what we're talking about. So if we have data that doesn't fit in with the message that we're trying to send, and there's an incongruity there, we won't look smart. We also all want to save money. And having the right data for the purposes and decisions that we need to take will help us spend less money unnecessarily. And again, a nice database joke, we want to complete transactions in the real and the database sense. So of course, bad data is simply not fit for its intended uses in operations planning or decision making. Now that we all agree on that, we're also going to assume going forward that when you're assessing your data, you have already decided what the purpose of the data is, and I am not here to help you assess what the purpose is. We've already hopped over that hurdle. So now we need to know what we are going to look at in order to make that assessment. What are some checkboxes or avenues that we can go down? And because I have a background in medical anthropology, or anthropology in general, I looked to different definitions for, well, what are other people already using to assess data? So the Informational Data Management Association is an international group, and they have these 6 dimensions. So these are really interesting things to think about with data. And I thought, I think there's more. And I found the Amsterdam Center for Health and Healthcare Research has another list that I also really liked. And this list is verbs. Great. This gives us 11 things to think about. And we've got 43 more minutes. But that's OK, because what I'm going to do is I'm going to interleave these. The data attributes and the verbs combine, and they can work in both directions. I want to let you know that we're not going to really talk about analysis today, because the analysis generally doesn't change the data, but acquiring or entering the data, cleaning the data, and storing the data have the ability to change the data. And because we're talking about the way the data can go bad, I think that's important. So the little red X's are things that I'm going to try to cover. You'll see that there's not going to be a whole lot of talk about cleaning data. And I find that really interesting because 60% of the time that most analysts spend dealing with data is spent cleaning data. So that is a whole talk all by itself. You can really break your data when you're cleaning it. So I'm just going to say use caution in cleaning your data. Additionally, cleaning your data is impacted by the choices that you need to make about acquiring and storing your data. So we're going to start with accuracy and acquisition. How can acquisition make good data bad? I had a really interesting experience, but first, of course, we need to talk about what is accuracy. And that is simply, again, not having the philosophical discussion of is truth a thing, but have we stored the correct value? And that could take any number of forms, right? So the first example, Flying Blue is an airline rewards program. Some of you have probably used it. And they wanted to know my date of birth to sign me up for their program. And I happily gave them that data, but I'm not giving you that data. So you just have to trust me that that really is my birthday. And then they said, oh, okay, this is the information that you gave us. And I said, no, that's not the information I gave you. And again, you just have to believe me that that's really not my year and month of birth. So I wondered, how did this happen? So I made a fake, I started over and created a fake account to see, well, did I mess this up? And it turns out that they had put December at the very top of the list of months. So this is one of the 3 hardest problems in computer science, right? Getting the positions right. So I continued checking, and I thought, okay, well, let me find and see if there's another month that will produce this off by 1 error. So I said, let me see if I can force it. And indeed, I could. This program told me that's not a real birthday. And August 31st is a real birthday in every year. So it was a really nice way to check that. So the reason that this happened was bad UX, bad UI. I had a bad experience and didn't know that the label of the months didn't actually match up to the months that they were going to record. How could I know that? I shouldn't have to know that, right? So what can we do? Test the inputs when we design the database. You may have to check every single potential input. You can automate that. Please automate that. And also talk to your front-end team, because a lot of what they're doing is they're connecting things to your database. So even if you've designed your database perfectly, and you probably have because you're all diligent, the front-end team may have some oversights. Another way to get bad data is accidents. So a very common accident, of course, is a cat or a toddler on your home computer. Scott Hanselman has a program called Baby Smash, and there's this program called PawSense. And what PawSense does is it detects cat-like typing and prevents you from putting in a string that could crash your computer, because it's probably happened to someone you know that a cat has jumped on a keyboard and done exactly the wrong thing and gotten you to a blue screen of death. So you can download this program on your home computer. And again, this can happen with errors in entry. A person who's an inexperienced user of a computer can input data that could be terrible. You can have unauthorized entry. Everyone has potentially seen the XKCD panel about little Bobby tables, and how you can, either through malice or ignorance, cause really big problems with data entry. And that's not necessarily going to affect just one piece of data, but it may lose your entire database or your entire system. So again, thinking about things that we can do, we can talk to domain experts to find out what are appropriate ways to input data, what are things that people might try to do to detect and exploit vulnerabilities in our systems, and what are ways that we can protect ourselves from that. Setting database constraints so that little Bobby tables can't be received as a piece of data, so that an error comes up and says, this is dangerous. We can also check anticipated versus actual values. So when we start inputting data, we can say, oh, this isn't at all what we expected, but we're getting a lot of things that we didn't expect. Do we need to go back and reset our entry expectations to match what's really coming in? And we always want to maintain security. There are some security talks here. There are lots of great security talks online. Maintaining security is something that's going to, well, many of these things are going to come up a lot. So now we're going to move on to completeness, since we've covered just a skim of accuracy and we have 37 more minutes. Completeness is obviously very easily impacted by acquisition and entry. Completeness is the existence or non-existence of gaps between expected data and the data we have. And because this is things to think about when you're assessing your data, you may not need the most complete data set, but you need to have an idea of how complete your data sets are. So there are some examples of having complete information. If you're playing a game of chess, all of the information is clearly in front of you. There are no hidden pieces. There are no made-up tactics that you've never heard of. Your player is less likely, your opponent is less likely to be able to bluff. So that's a really beautiful case of having all the information. The real world is a little bit more like a game of poker, where you have some of your information and you have an idea that you know what you don't know, and then there are some things that you don't know, depending on your skill as a poker player. And this is very important with data. So we want to think about sampling correctly. Did we get enough data from enough different kinds of people, or enough data from enough different, let's say we're thinking about climate change. Are we only sampling data from one area or from one time of the year? The more broad our data collection may be, the better likelihood that we have enough data. We also want to make sure that we have a complete understanding of our business problem, because knowing how much data to collect requires, of course, as I said before, that we have already decided what is the purpose of having this data. And of course, it's possible that the data simply isn't available or isn't available yet. So things that we can do about the completeness problem is, of course, again, we can approach our domain experts and say, what do we need to know before we begin collecting or acquiring data? And we can also find additional data sets. You can find, either for purchase or open source, a lot of different data sets that may not on the surface be clearly about what you need, but they may contain a column or two that are relevant to your concerns. So next we move to the only time we're going to talk about cleaning very directly here, and this is with completeness. And I find cleaning for completeness really important because it turns to be what most people don't think about. It's very common to think we need more data, need more data, but it's not common necessarily to think we have too much data. We have a column of data that contains personally identifying information. We have a column of data that contains sensitive financial information. We have a column of data that contains national secrets. We can just jettison those from our databases in a lot of situations and protect ourselves from leaks, and that's really great. So relevance and size are things to consider. If this data isn't relevant, why are we spending the money to store it? Why are we spending the query time to skip over it? Why are we partitioning around it? Why are we keeping it? Or why are we keeping it in this particular place where we're keeping it? So we may trim or filter our data as necessary. This may happen because the data set is simply too large. We may not be able to afford the storage for the entire data set. The data set may have irrelevant bits, like years that we don't find ourselves concerned with. We may have the unnecessary columns that I mentioned before. So things that we can do about this, in the beginning, we can import selectively. If you're taking a CSV and loading it into your database, you don't necessarily need to take all of the columns. So having those conversations I mentioned earlier with your domain experts can give you some guidance on maybe not having to have it all to begin with. Screening that data carefully. And again, trim and filter as appropriate if you do end up with things in your database that you find later that you don't need. Completeness and storage. This is going to sound a little bit familiar because I've just touched on a little bit of it. But you can have different size storage options, obviously. Some of them are going to be more expensive or not available. You cannot fit 50 pounds of pecans in a pecan bag designed for 25 pounds of pecans. I know that every year somebody loses data because they haven't made sure that they have enough storage for it. This historically has been a problem with data's physical size. We're seeing it becoming a problem with location. If you're storing your data in the cloud and you have purchased storage on, say, the East Coast, but you haven't purchased that backup plan of also having your data in another data center on the West Coast or somewhere else in the world, and the entire East Coast data center of your cloud goes down, where is your data? It is gone. So storage is very important for completeness because you may literally lose everything. If you're not correctly assessing your storage needs, it can be very tempting in the early stages to say, well, we only need 1 terabyte of data, and that's really great until you need 1.1 terabytes of data, or have 1.1 terabytes of data. And the other is also true. It's possible to simply have too much storage. That can be very costly for a business. So if you only need 1.1 terabytes of data storage, maybe don't pay for 5, or don't pay for 5 yet. Also, as I said, be sure to choose the location and type of storage appropriately for your team's needs. And you may want to be careful that you're not accidentally dropping tables, columns, or databases, because that can lead to some very obvious completeness problems. We want to be realistic. We want to have backups, and we want to trust our users. We want to not just say to people, I trust you not to drop the database, but also have permissioning that's set up appropriately. Completeness and cleaning. Going backwards a little bit here, there was a financial institution many years ago that wrote a letter to users with lots and lots of money in their accounts. And what they were doing was they were selling a new product. And there was some incomplete data where the name of the client was unknown or not in the field where it was expected to be. And a programmer said, I will make a placeholder. This letter was mailed. And this letter was some really good publicity. The company needed to send a team of salesmen out to make some we're very sorry and terribly contrite visits with fairly nice gifts. And one of the companies that received this letter found it so funny that they framed it and put it on the wall. So it was certainly memorable. But what was even more interesting was companies who had not received this letter heard about it and called and said, we have a lot of money in our accounts with you. Why did we not get a Dear Rich Bastard letter? So it's, the phrase, there's no such thing as bad publicity, may be true, but maybe don't swear at your clients if you can help it. So instead of choosing placeholders that may be offensive, choose another way to make a placeholder by thinking of something that's clearly going to throw a human being into saying, I shouldn't mail Shruggy Guy. And remember, when you're making Shruggy Guy in Postgres, you need an extra slash. Otherwise, he's an escape character. The story is very common in that null is a problem. We'll find in life very, very few times that we have null or a forced not null where there isn't an associated problem. I could talk about that for an hour, but Leticia is much better qualified to talk about that, so go see her talk about null. It's very helpful. So like I said, null is a black hole of data problems, and go listen to Leticia. But what we can do is we can document our code. The programmer who used Dear Rich Bastard as a placeholder didn't document that he had done that. So when he left the company and someone else took on this project, they were very surprised by this undocumented surprise. Of course, be careful with null. And finally, make null appear as something more noticeable. Additionally, sometimes one single tap of the space bar can return as looking in your data set like null. be aware of that as well. So then we go on to conformance. What is conformance? Is the data in a format that is expected and acceptable? And this is related to something that we'll see a little later as well. So first we're going to address conformance and acquisition. So it can be very hard to take some kinds of data and get them into a database. If you want this to be machine readable, how do you do it? I'm sincerely asking you. Please find me later and tell me how you make this machine readable. It's a phenomenally interesting problem to me. Currently, what most organizations are doing is a human being is reading this terrible handwriting, typing it in, and then they're either taking that image and putting it into a database, or they're just describing it, or they're discarding that data. So finding ways to get acceptable representations of data is certainly a challenge. You may find errors in entry, whether that's an error in the decision even to transcribe it, an error in the decision to discard it, or an error in something like spelling or intent. You also have limitations in data collection and availability. A lot of those kinds of data collections it takes a long time for someone to make a drawing or write something out by hand, and so they may not collect as many pieces of information in that format. So you may want to consider giving your respondents a different way to respond. And finally, if you need to transform from any one data type to another data type, you can end up with losses in meaning, losses of information. So things that we can do about it: test our inputs when we design the database. Go ahead and run the process through of taking a notepad with an image and handwritten words and try and get as many different people to take that same piece of information and see if you get some consistency. Have multiple entries of subsets of data after you've done the testing. When you're in your production environment, you've got to have the resources to have 3 different people, not every single piece of data, but check for discrepancies. And again, search out additional data sets. If there's a way to get this information that's got less friction points for your team, go ahead and use that other data set if it's appropriate on enough metrics to make that trade-off worth it for you. More conformance and accuracy. The money data type, please don't use it. Years, very tricky across databases. So some databases have a year 0. So if you're changing databases, be aware of what's going to happen to your time. I saw you gasp. I'm so sorry. And money, again, is also a challenge. So don't use the money data type. Find the numeric data type that best represents the kind of numbers required for the money that you have. Some money types, some currencies use more decimal places than others. So, an integer or just 2 decimal places or maybe more might be better suited for your needs. And again, I don't know what the purpose that you're using your data for, so I can't tell you which of these you should choose because these choices will be different with every purpose. So you're assessing, is what I have going to work for what I want or need to do? Be aware of calendar challenges. There is a particular date in Postgres that I knew off the top of my head an hour ago and can't come up with that just does not show up in Postgres appropriately. It's Joe, do you know the date? No, okay, that's fine. Again, don't use the money type. And I say that as though I'm some sort of authority, but 6 people will come to me and say, I have a really great time using the money data type, and that's really great because you've explored that and it is using data that fits your needs. That's wonderful, but for most people, it's not an appropriate application of the SQL standard. Also, know which jurisdictions recognize things like leap seconds or utilize daylight savings time. Even in America, we have issues with daylight savings time being different in different counties in Arizona and some other different places. But there literally are countries that don't use leap seconds, which can really wreak havoc on your entire database. And offsets. So if you've written an app that's taking care of an offset and you're also having Postgres do a time zone offset, when they come together, they can create a lot of confusion for you or your users. And of course, sometimes data is machine generated. So there are a lot of potential problems for machine-generated data that are easy to overlook. So things like improper machine calibration can lead to a long string of values that simply couldn't even be valid. They are perhaps all null, or they are perhaps all off by a factor of 100 or 1,000, or perhaps someone has calibrated the machine to create a text string when it should be making a date field, or to give you a date field when it should be giving you a temperature. So another thing that happens is a machine is generating the data, and then a person is generating a visual on that data, and they're making an incorrect assumption about it. This is very common in hospital settings where you're hooked up to a blood pressure monitor or a breathing monitor, and a nurse will come around and write down the number, and then that number gets written down, and her handwriting gets transcribed by someone who puts it into a computer. And maybe that someone is herself, but maybe it's another person altogether. So you can see a string of not just, if she makes a mistake reading the machine, that's very relevant to hear. If she thinks she sees 98 when really something is 78, she's introduced an error. But there are other ways for machine-generated data to not be perfect or fit for use. So we can set our database constraints to not accept strings of words when they should be in a date format, and to throw an error to let us know that someone needs to go check on that machine. We can also find ways to test our machine-generated data in addition to those constraints. And we definitely want to make sure that human beings who are interacting with the ways that data is generated are trained in, is this an acceptable and usable number? Because it's very tempting to just say, I wrote down what the machine told me, without a grounding in what is reasonable for that machine to tell you. So you can end up with weeks or months of inappropriate machine-generated data because a lot of people trusted the machine. Conformance and acquisition, we end up with a lot of null things. People get really creative when you force them to not rely on null. Null is a very big problem. Again, Leticia will tell you a lot more about it than I am going to, but my love of not null is being able in a QA position to find all of the creative ways that people find to tell you that they don't know. And sometimes they tell you things in ways that look a lot like your data. If you force them to give you a string of numbers, they may make up a temperature or a street address that looks 1, 2, 3 anywhere lane. There is in the United States a lane named Anywhere. I hope there's not a 1, 2, 3 house number on it for their sake. So null, even Tony Hoare, who put null into computers, regrets it. He says that it has created billions of dollars of losses and problems. But I like null. So definitely come to me with your null stories because I will appreciate them. If you force your data entrant to provide a response but don't give them an acceptable way to say, I don't know, they will make up their own. So in data entry and survey collection, you provide a radio button or a checkbox that says, I don't know, or it's not relevant, or this information doesn't exist. Those are 3 very different selections, and it's really common to see null or NA used to catch all of them. And in that case, the contemporary understood definition of null as there is no data fails. So make sure to provide sufficient ways to capture what they need. And also you can, again, consult domain experts. What are we actually expecting people to provide us? And either allow people to type in a response or select some other way to give you information that is usable and is in conformant. And also practice good knowledge elicitation. Make sure you're asking a question that makes sense, that your respondent really may know the answer, but if they don't understand your question, then they don't know that they understand. So it's a very interesting quadrant of knowledge, the known known, the unknown known, the known unknown, and the unknown unknown, right? So if they're not understanding your question, they don't know that they know the answer, and that's a problem because now you don't know the answer. Storing your data can also create some conformance problems. Boolean is my favorite example of this. I was talking to someone very recently whose organization stores Boolean values as Boolean in some parts of their data structure, as integers in another part of their data structure, and as strings in a different part of their data structure. What we have on the screen are all of the things that you can put into Postgres in a Boolean field that Postgres will accept and recognize and understand. If you're using an integer field or a varchar field, what you end up with is the possibility of, instead of having people say 0, 1, or 2, they may say 0, 1, 2, 3, 4, 5, 100, especially if you've given them what you're calling a Boolean field that can't be null. But you've allowed them to have numbers without constraining your database. And the same is true of strings. So text fields and integer fields are two of the biggest ways that this becomes a problem. And the best things to do about it are to use the Boolean data type and enforce that. So when someone comes to you and says, we have a need to do this. And again, sometimes you end up with data sources that you have received. You don't have any control over how this data was collected, so you can do transformations. With the received data, you can try to cast text or integers to Boolean, but you very often will find users of your data who say, I need the output of these Boolean fields to be something other than what Postgres will give me. And in that case, you can cast the Boolean to text or to integer as is appropriate for your end user. So this is something that comes from both sides. So the next thing we have is consistency. And consistency is really two things. If the database is making changes to the data, am I going to be surprised by those changes? And the other part of consistency is, are there conflicts between data? And this brings us back to that philosophical conversation that we're not having about, is there such a thing as truth? Because in the real world, there very often is a conflict between pieces of data. But we're hoping that there are not. So you have an expectation, and you know that stormtroopers are tall, and then you find a stormtrooper that is very short, and you are surprised. That was a Star Wars reference. I'm very sorry. But you also may find that some of your data has, like our gentleman in black here, gone over to the dark side. For a further database joke, something has changed about this piece of data, and now it is no longer fit for its initial purpose, and it has possibly taken on a new purpose that is not your purpose. And that can be very damaging for a lot of different cases. So this happens sometimes by selecting different data sets for different areas of your database. You have a customer database, and you have, or a customer table or a customer namespace, and then you have a sales namespace, and you're getting, say, your emails from different sources. So you're joining together what you think is the same customer, but they have two different email addresses. Well, now you have an inconsistent email address for that customer. How do you decide which email address to send information to? Or do you run the risk of annoying your customer and send the email to both email addresses? This is a decision that you're going to have to make depending on what your purpose is. And you also may end up with a database or a data set that you inherited from someone else or purchased from someone else that already had inconsistency in it. And that's unfortunate, so you have to find it. So luckily, you can make choices about your received data sets and coalesce them appropriately. So when you're selecting for your first not null value or your first not null, not zero value, you can try to be sure that you always put them in the same order. You can also use documented reproducible methods to clean your data so that the second round of cleaning your data with a different method doesn't leave you with a different value. And you can also set your database constraints to check consistency. If you need column A to always be the same in table 1 as it is in table B, you can say, tell me, and your database can do that. Consistency in storage is also a really, really interesting problem space. Granularity can be really hard to deal with, and what we mean by granularity is really well explained by capturing age. If I ask you for your age range and you say 29 to 34, 35 to 42, that's really great. I know a group that you belong to. But if later I decide I actually need to know your actual age because I need to make different distinctions or finer grained distinctions, or I have enough data now that I can say something about 19-year-olds and maybe they're different than 21-year-olds, but I've lumped them all together. If you decide to change the granularity, you started with, or rather you now want a very fine granularity. You want each individual age. But instead what you have is a very large granularity that's never going to make it through that sieve. You might end up with this by changing your data model. You might end up by changing your database system. If you move from another management system over to Postgres, you may need to keep an eye on, is the Postgres database designed by the domain experts with an understanding of the granularity that we're going to get? Or is it designed with the granularity that we want? And finally, data simply may be transferred inappropriately. So what we want to do, of course, is take our first design of that data model and be very, very careful when we do it and think as far into the future about what our potential needs might be. And of course, designing our data model depends a lot on the research, the data that's available to us. So if all of the data sets that we can acquire only have that chunky granularity, maybe we make a column for future granularity or for aspirational granularity, but maybe we just deal with what we have. Again, it's really going to depend on what our purpose is. We're going to speak with domain experts to find out, are we likely to ever really need that granularity? And again, use a new column instead of changing an existing column so that when we do an analysis, we can explain these are the changes that we made. Consistency in acquisition. When you're getting data in a medical setting, if you go to the emergency room, you're likely to be able to provide the people who are communicating with you information about who you are and what's going on. But frequently, people end up in emergency situations, not just with health, but in a lot of situations where they're not able to impart the information that they have. So there are blank spaces. You end up with John Doe or other pieces of information that are missing. And the provider may make a plan to collect that data later and then put that new data in another place. So you can see how your consistency problem is. In one place you're listed as John Doe, and in another place you have a name. In one place you're listed as not having insurance, in another place you are listed as having insurance. If you've ever changed your insurance provider and kept your same healthcare provider, sometimes getting them to get your new health insurance information into the system is difficult. Additionally, we want to ensure consistency in things like who is allowed to input this data and is their identity connected to the data. In my background in medical offices, it's very common for people to have sort of a catch-all login where it's just staff. And then there's no name attached to the person who made a clinical note or a billing note. And you want to make sure that those things can be captured. So again, we're back again to improper database constraints. We're back again to database systems. The management system may be changed. And if data isn't entered appropriately, if someone simply makes an incorrect spelling, you could have people in the same system who are duplicates, which we'll see in a few minutes, and have that be incorrect. Again, the emergency situation. So there are some things that we can do. We can have access to multiple data sets for emergencies. Electronic medical records are becoming more popular, and this is really helpful because if you have an identification on you, they can, in a lot of cases, find some bit of your electronic medical record. We always want to speak with domain experts to plan our permissioning on our databases, and we want to let people know when a change happened. Did we used to have the staff signifier, but now everybody signs in on their own, and now we can really see the consistency in who is putting in the data. And Postgres, of course, has really great concurrency control, which covers a lot of issues of consistency. There are, in fact, several great talks about concurrency in Postgres. Next, we deal with timeliness, which again is a two-pronged item. Can we find more recent data that is properly fit for doing what we need it to do? And is the data that we have accessible at an appropriate timeline? So acquiring your data certainly has impacts on its timeliness. Google Maps in the springtime lost a neighborhood. Well, what they did was they renamed it. They renamed a neighborhood Medical Park because somebody found an old map in a physical storage space that had this neighborhood named Medical Park. It was a map from 1990, I believe. And for some reason, throughout the acquisition, the entry, the cleaning, the analysis, the consistency, and the accuracy, this made it onto not just Google, but several other sites. So what we see is that sometimes you discover a new data set or what's new to you, but it turns out it was actually old, and it can be easy to miss when was this data collected. If the metadata isn't existent on your data set, you have a lot of potential problems, but timeliness is certainly one of them. And sometimes a newly created data set, something that was perhaps released or collected last week or last year, is something you don't have access yet or don't know about. And sometimes, as I said in the metadata, you may just not know or know how to find out how old is a data set. So what you want to do is check the provenance of your data. You want to see, can you find other data sources? And maybe you need to combine data sets, but you also want to identify if more data really is needed. Sometimes older data is perfectly fit for what you want to do with it, and you don't necessarily need to hunt down something additional. So again, with acquisition of data, you have sometimes machines are generating our data, which I find super fascinating. Problems with the timeliness of this can deal with infrastructure limitations. So that's things like cloud cover and you couldn't get satellite update, or you didn't have enough battery power. So we want to make sure that there's enough storage on the machines that are collecting our data, and we want to have an offline first design so that we can get that upload on the next attempt. Storing our data has certainly timeliness implications, because we know that if we can't get to our data quickly enough, if the lock is rusted shut, then we're going to have a problem. So we also can see this with trying to query very large data sets where the query takes a long time to return and our application is hanging and our customers are disappointed. They may go to a different customer opportunity. And we also can see that sometimes data security that is too robust may prevent access. And then sometimes in our storage, we have stale data. So things that we can do about this as our little tiny baby elephant database grows up into a great big elephant database with our increased storage, we can make or choose better indexes to increase our query time. We can use partitioning to, again, speed up our query time. Previously, we talked about completeness and the opportunity to store less data. Just because you have it doesn't necessarily mean you need it, and not having it means you don't have to search it. You also may want to evaluate your roles and your users so that maybe some people have access to more of your information. And very importantly, if you're using materialized views, you must make sure they get updated. Because if you've got a materialized view on a database that gets a lot of additions to it, you don't want to be serving last week's data. And you want to do it in transactions so that you don't have two queries running at the same time that finish at different times and give you different results. We're in the home stretch. We've got uniqueness. And uniqueness covers acquisition and storage very, very well with the question, are there duplicates in the data set? Sometimes yes and sometimes no, right? So do we have a duplicate in this data set? And this is a very hard question to answer without domain knowledge, because maybe banana is a candy or some other kind of food product that's banana flavored. But it may also just be that somebody got really busy and distracted with the NNA keys. I can't tell, and you may not be able to tell either. So you need to be aware that things that look like duplicates may not actually be duplicates. But then you have things that look like they're not duplicates, that are duplicates. You may have banana and, oh wow, I just literally lost that entire thought. I'm very sorry. But we see this when we make assumptions about domain. So if we assume that banana and banana are the only two things in the grocery store that there is only one thing in the grocery store that could be that, we may have a problem. But it could be an entry error. And of course, one of the two hardest problems in computer science is naming things. So that's a bigger problem than just our domain. Everybody has problems naming things. So it's very, very hard to make it clear that these are in fact different items or they are the same. And then of course we have duplicate entries. So it's possible to give a primary key to banana with its particular item number and its particular expected weight ranges, because you're not going to allow a 40-pound banana because you set the constraints on your database correctly. And then you're going to have a problem when somebody comes in for a party and wants to literally buy 40 pounds of bananas, so you have to bring it up as 41-pound purchases of bananas. I've seen this, not actually with bananas. But then you may make a second entry for banana, and you are actually meaning banana, but you forgot that you had left off, at the spot right after banana. So you picked back up and you assigned a new primary key, and your constraints allowed you to have two identical items, but they have a different primary key, so your system thinks that they're different. Check with domain experts. I think this is probably our big takeaway today. Check the entry. Make sure that you have a subset of the things that your data entry team is doing and get them correctly. Set your primary key to have appropriate things. Don't just assign one, but maybe try to find a natural key. And clean information based on information, not on what your assumptions are about your data set. So the last thing we're going to cover is validity. And validity is the question of form, syntax, and type being correct. So obviously, we really would prefer not to have dates stored as texts, and we would prefer not to have numbers stored as text, and we would prefer not to have text stored as digits if it's appropriate for our purposes to have that. But we also want to know if the data has the potential to be accurate. So for instance, in acquiring our data, if we have a patient and we know her date of birth and we've taken her temperature with a thermometer, we know that she could possibly have a temperature of 101, but she should not be 970 degrees in either scale. Be a very warm, very dead patient, right? And that appears to be an entry error of missing a decimal point. The next entry of 111 for a temperature appears to simply be someone saying, I don't know what the temperature of this patient is, either because I had a broken thermometer or the patient was unwilling to have their temperature taken or I didn't have time. But those are in our database, and it's concerning if we're trying to measure or say something about the temperatures of our patients. Are these pieces of data equivalent? In a lot of cases, no, but Excel will do you the very handy favor of stripping those 3 zeros for you and leaving you with simply 861, even if that's not a possible answer in the range of what your expected data is. So how this happens, we end up importing data from various sources with different ideas about what they think appropriate information is. We've selected an improper data type, which sometimes could be an improper data type. We've made format changes to our data. We've forced a not null, or we've made errors in our data entry. So what we can do is select data type columns. We can set the values for the constraints, and we can figure out a solution for null, which I'm hoping Leticia will provide you enough guidance on that you aren't disappointed in how little information about null you got from me. So again, here's the matrix that we used and discussed today. And if you have any questions, we can take them in the hall because it's time now to move to the next room. So thank you all for joining us for that very fast tour of data quality. It is one of my favorite things about data, is seeing what's good and seeing what's less good. So thank you again.